Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, node balancers, and a 40 gigabit public network, all controlled by a brand new API, you've got everything you need to scale up. And for your tasks that need fast computation, such as training machine learning models and running your continuous integration, they just launched dedicated CPU instances. Go to pythonpodcast.com/linode, that's Linode, today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. Taking a look at recent trends in the data science and analytics landscape, it's becoming increasingly advantageous to have a deep understanding of both SQL and Python. A hybrid model of analytics can achieve a more harmonious relationship between the two languages. Read more about the Python and SQL intersection in analytics at mode.com/init, that's INIT. Specifically, we'll be focusing on their similarities rather than their differences. And you listen to this show to learn and stay up to date with the ways that Python is being used, including the latest in machine learning and data analysis. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, Corinium Global Intelligence, and Data Council. Upcoming events include the O'Reilly AI Conference, the Strata Data Conference, the combined events of the Data Architecture Summit and Graph Forum, and Data Council in Barcelona. Go to pythonpodcast.com/conferences today to learn more about these and other events, and take advantage of our partner discounts when you register. Your host, as usual, is Tobias Macey, and today I'm interviewing Robert Hodges about how the PyData ecosystem can play nicely with data warehouses. So, Robert, can you start by introducing yourself?
Hi, my name is Robert Hodges, and I'm CEO of Altinity. We offer commercial support and software for ClickHouse, which is a popular open source data warehouse. Beyond that, I have a pretty long background in databases. I started working on databases in 1983 with a system called M204, and ClickHouse is now database number 20, I think, because I'm kind of losing count.
Yeah, after the first few, I'm sure you probably stopped bothering to keep exact track.
Well, every time I count, I keep finding ones that I forgot about. And it's definitely, it's been very variable. For example, I worked for over 10 years with MySQL. Then there were others like DB2 where I used it for a day and decided I hated it. So it still counts.
And also, databases is in some ways a bit of a nebulous definition where if you squint enough, different things can be considered databases that you might not think of at first blush.
Absolutely. And I think what's interesting over the last, perhaps, say, 10 to 12 years is the range of things that we properly consider databases has increased enormously as people deal with different kinds of data, different amounts of data, and different problems that they're trying to solve when they analyze the data. Those have all driven sort of a plethora of different kinds of approaches to databases.
And do you remember how you first got introduced to Python?
You know, that's a really good question. I think what it was, and I can't remember what happened, I read an article that said, that a long time ago, that said Python was so beautifully designed that it is something where you would be up and running and productive in about 4 hours. And so I thought, okay, that sounds good. And I went and tried it. And it did seem pretty easy to use, but I didn't program with it at the time. I've got introduced to it at an industrial level at VMware about 2.5 years ago, where I was working on a project doing tools for one of the VMware cloud products. And I was sort of the architect for a group that was developing open source Python APIs. And that was where I really learned how to use Python well, learned how to do things like actually properly program modules, do documentation, do setup.py, things like that. So that was really my full education in it.
And so for this conversation, can you start with giving a bit of a quick overview about what a data warehouse is and some of the ways that it differs from a quote-unquote regular database that somebody might think of for anybody who isn't familiar with this space?
Sure. So I think that it helps to start this out by defining what we mean by a regular database, because I just said, as I've referred to, and as I think many people know, there are many types of databases. So when people think about a database, they commonly think about something like MySQL, which stores data in tables. And the tables consist of, so that means that there's a set of columns that each table contains, and then the data are actually stored as rows. And this is the same data structure that you see when you work in Excel. So what we, generally speaking, we call that kind of database a row-oriented store, which means that when you actually look at how the data are stored on disk or on SSD, as the case may be, as well as the way that they're accessed. We go get them by rows. And this type of database was one of the earliest that was developed, and it's very well optimized for things like managing data in a bank or for managing sessions on a website, because there's a lot of little change, there's a lot of little updates, and we can go to the row, change it, put it back, and so on and so forth. Now, that kind of database has a problem, which is that as you get to very, very large amounts of data, the fact that it's efficient for update leads to a trade-off that it's not particularly efficient for reading. And one of the reasons is that if you wanted to, for example, had a data warehouse, like a table in your database that contained taxi rides, and one of those fields was the number of people that rode in the taxi, and you wanted to just take the average, you would end up reading and pulling into storage all the rest of the rows just to read that one little tiny field. So as a result, data warehouses began to develop in the 90s, and they took a different approach to the way they organized data, which is that they organized it in columns. So you could have your billion row table, and you might have your field, which contains the number of people in the taxi. That would be stored in a single column. And the idea is that the data warehouse is, in this and many other ways, optimized to read data very, very efficiently. So if you want to do that average, what you're going to do is you're going to read down this column very quickly. And on top of that, the data warehouse typically has optimizations like that. That array of data, if you will, is going to be compressed. And the compression algorithms can be extremely efficient. So for example, you can get 200-fold compression on one of those columns, depending on what the values are. So it compresses down to a very small amount of data. Plus, we use very sophisticated processing techniques so that we can take advantage of what are called SIMD instructions, single instruction, multiple data, that allow us to operate on multiple values at a time when these things are loaded onto CPU registers. So this type of database, which is optimized for read, is now generally what we know of when we talk about data warehouses.
And there are some cases where people might end up using a row-oriented store as a data warehouse just because that's what they have close to hand. I know that I've seen it with things like the Microsoft SQL Server, and I've heard of people using Postgres for that purpose if they have a small enough data set where they're able to perform their analytics, but the pattern in which they're using it is more along the lines of a sort of more read-oriented than write-oriented, so that they can run their analytics off of it without necessarily interrupting their application databases.
Exactly. And in fact, what I started to notice perhaps 12 years ago when I was working with customers was that you would see, I ran a business that was actually focused on, as it turned out, clustering for MySQL databases. And we had people that ran pretty big MySQL installations. But what you would see in their data sets was they might have 200 tables in a database. But when you actually went and looked at how big the tables were, they were probably one or two, which turned out to be extremely large. Sometimes they would contain hundreds of millions of rows. And then the rest of the tables would tail off really quickly, because then they would be, things like customers, currency values, or things like that turned out to be small numbers. So what has happened is that people have done exactly as you described. They start out using MySQL, Postgres, Microsoft SQL Server. They get to the point where they have about 100 or 200 million rows, and that's the kind of the point where it becomes very, very difficult to do these read operations on the row-oriented database. Not only does it disrupt the operational work that's going on, so for example, trying to update the tables, but the other thing is it becomes extremely slow. And the difference in performance can be staggering. When you have 200 million rows in a MySQL table, the difference between the performance there and running in a data warehouse will be a factor of 100 sometimes, even more in some cases.
And on the other side of what we're talking about today, there's the PyData ecosystem, which encompasses a large number of packages, but at the core of which most people will consider things such as NumPy, Pandas, maybe the Jupyter Notebooks format, and probably things such as scikit-learn, or maybe some of the machine learning libraries. And I'm wondering, what are some of the cases where those libraries on their own aren't necessarily sufficient for being able to process data either efficiently or where you might need to lean on something such as a data warehouse in conjunction with the PyData stack for being able to achieve a particular project?
Yeah, that's a great question. So I think the biggest thing that I see is that, well, first of all, I want to say that these tools, the PyData, that whole ecosystem is really inspiring because it has such a wealth of operations that you can do on matrix and vector-oriented data. Plus, it's coupled with really great machine learning as well as visualization tools. So it's a really, really great ecosystem. But I think the single biggest thing that I hear about is people, probably first of all, people just complaining, hey, my data don't fit into memory anymore. And so what you end up seeing, at least in my experience, is that when you're running models in Python, you'll end up sampling because you actually can't hold all the data in memory. So you just load a sample, say 10% or 1% or something like that. You train your model on that, or you run your model, or you do whatever operation that you're doing, you'll do on a small fraction of data. And the basic reason is you can't put it all in memory and process it at once. And I think part of this is because I think this is happening for two reasons. One is that Python, bless its heart, does not have a particularly efficient way of representing data in memory. This is actually common to other systems like Java. It's not a Python problem per se, but it's just that when you materialize objects in memory, they're not necessarily using memory layout as efficiently as they can. The second thing, and I think this is maybe more important, is that by default, Pandas wants to have everything in memory at once. So if you have a matrix or like a Pandas data frame, it's going to want to have the whole thing in memory. And there's not a notion, for example, at least by default, of being able to stream through data. And so that can also be a problem when you're trying to deal with large amounts of information.
Yeah, for a lot of these out-of-core systems, people might start to lean on things such as Dask or the Ray project for being able to scale across multiple machines and multiple cores, both for the memory issues that you were laying out, as well as some of the issues with dealing with embarrassingly parallel computations. And I'm curious how that plays into the overall use case for data warehouses and some of the other ways that those broader elements in the ecosystem can also help in terms of managing larger data volumes and also where the data warehouse can benefit.
Yeah, I think that's a great question because because I think what you see happening with projects like Dask, at one level you could say, hey, this is Python kind of rediscovering or re-implementing MapReduce, which, the notion that you can do distributed processing, you have a lot of storage across a bunch of nodes. But I think more particularly what I see happening in the PyData ecosystem is that people are beginning to replicate in Python things that are already solved in data warehouses. And I'll give you a couple of examples. The data warehouses like Vertica or ClickHouse, the one that I operate on, are very good at spreading data across multiple nodes. So they have the ability to break it up into, we call this sharding. So break it up into pieces that can be spread across nodes and then run the query in parts and join the results together or aggregate the results together before they return. Another thing we can do is we can replicate the data. So as the number of users on your system span extends upwards and you're beginning to ask a lot of more questions concurrently, the ability to have replicas allows you to scale the performance very efficiently. So because different queries can run against different replicas. So I think this is I think what's happening is that as these systems like Dask start to emerge, it's time to ask the question, do we want to implement this entire thing in Python, or do we want to actually go look in the SQL data warehouse, see what they've got there, and maybe begin to sort of shift the boundaries a little bit between what we do inside the database and what we do in Python.
And in terms of the actual data warehouses themselves, you've already mentioned ClickHouse and Vertica, and there are a number of other ones out there, such as Snowflake, that's a recent addition, and then there are also various things that you could potentially consider in terms of data warehousing that are bordering the line with data lake, such as the Hadoop system or things that the Databricks folks are doing with Delta Lake. And I'm wondering, what are some of the main axes along which the different data warehouses try to differentiate themselves, and some of the considerations that somebody should be thinking about as they're trying to select a platform for moving forward with?
Sure. I think we can definitely divide the market up into some important important segments. So for example, you mentioned Snowflake. That's a cloud data warehouse. And there's a family of data warehouses that are really cloud native. They are always they may be tied to a particular cloud implementation. That would be the case with things like BigQuery on Google Cloud or Redshift on Amazon, or Snowflake, which can span clouds, but depends on the underlying cloud capabilities to work. So those data warehouses have great capabilities. They have very full SQL. They're well funded. They have very good SQL implementations. They also deal. One of the things that particularly Snowflake and BigQuery do very efficiently is they decouple the processing from the storage. So, for example, one of the things I like about Snowflake and their processing model is that you can have a big business and you can have a couple of organizations. They can each do queries on the same data, and the way that Snowflake handles this is they spin up what are called virtual data warehouses, which are the compute part. Each business unit will get their own virtual data warehouse, and they can go to town on this underlying data that they're reading without interfering with each other at all. So that's one class of data warehouse that I think is really important to look at. And I think where people tend to make choices in that direction is if I think probably the single biggest factor is, has your business just decided, hey, we're going to be on Google? If you are, then there's probably a pretty strong argument for looking very closely at Google Cloud or Google BigQuery, because you're already there, your data is stored in object storage. So that's one big class. I think another important class of data warehouse is the traditional data warehouses, like of which Vertica and Microsoft SQL Server and Oracle are sort of all play into this. I think the most interesting one is Vertica. That was a very innovative column store. They're doing some interesting things in terms of separating compute and storage. They've now got a cloud version of it called Eon. So that's another one to look at. I think they have good capabilities. I think the trade-off there is they tend to be expensive to operate. And it's not just because they're proprietary software with expensive licensing. They tend to require pretty good hardware to run on. And then you have data warehouses like ClickHouse. ClickHouse is kind of an interesting case. It's open source, Apache licensed. It's also more like MySQL in the sense that it is, even though it's a column store and has all these properties that make it run very fast for reads, it's very simple to operate. And it's also very portable across a lot of different environments. So for example, we run ClickHouse on everything from bare metal. We have a lot of people who still run their own data centers or lease space to run their equipment, to Kubernetes, all the way to VMs running in the cloud. So these are three different classes of data warehouse. And I think depending on your use case, where your price points are, what is it you're looking at doing there, each of them has virtues and also drawbacks.
And I'll also just point out that you and one of your colleagues was also on my other podcast talking a bit more deeply about ClickHouse, and I've also covered a number of these other technologies on that show as well for anybody who wants to go further down the rabbit hole.
Exactly, and it's a great rabbit hole. We like living down there, so I'm sort of out in the open air for a little while this afternoon.
And so once somebody has selected a data warehouse, they've got it deployed, and now they're looking to actually populate it with data and be able to start integrating it into their overall workflow. What are some of the ways that the PyData ecosystem can help facilitate that process of getting data into it and making sure that all of the data is appropriately cleaned and the schema is matching appropriately? And then also in terms of ways to ensure that the schema is optimized for the types of analytics that you might be doing, and just some of the other considerations going into the design and implementation of the data warehouse.
Yeah, that's an interesting question. So I can give an example from our work on ClickHouse, which I think illustrates some of where Python fits in. So a lot of data in the real world is in CSV. So comma separated values. And it turns out that Pandas is pretty nice has good ability to read CSV. It's relatively tolerant of different formats. And so one of the ways that I've actually seen customers reading or using Python to help with ingest is that they will actually use Pandas to read the CSV files, clean them up, write them to Parquet, and then we have the ability to ingest Parquet directly into ClickHouse. So that's an example of where Python is kind of there to help in terms of the data cleanup up front. I think more generally, one of the things, and this is not true of everybody, but I think that in the systems where we see very large amounts of data being ingested, actually, I think what happens is that Python, you kind of stay out of the way because, for example, about half of the people that we work with ingest data from Kafka. So the ClickHouse, like some other data warehouses, can actually read Kafka queues directly. So that's an example of where you don't actually need an intermediary. And if you want to do cleanup, you'll actually wait till it's in the data warehouse, and then you often use SQL to clean it up. So, and that's a very common use pattern. I think the other way that data gets loaded is that you read it from object store. So, for example, if you use Redshift, it has this great command called copy, which is used to read files, but it's been adapted in Redshift so that it can read data directly out of S3. So where the PyData ecosystem would fit in is PyData might be the stuff up front, for example, that's scraping the data off other online systems. So, for example, I did an application with students from University of California, Davis, where they built scrapers that would go search for prices for web resources like EC2 on Amazon. They'd search for them on the web. They'd put them into S3, and then we would read them into the data warehouse from there. So if PyData is involved, it's really at the front end of collecting the data and putting into object store. Those are two big ways that data gets into these systems at scale, and Python is sort of helping along the way.
And on the other end, once the data's already been loaded and you're looking to do some sort of analysis or maybe even train some machine learning models based on the data that's there, what are some of the ways that an analyst or data scientist might use for interacting with the data warehouse?
Yeah, I think that in this particular case, I can really only speak to examples from ClickHouse, but I think these are relevant for other databases. So, for example, one of the simple ways that you can interact with the data warehouse is you just fire up the Python client and sort of build a simple application on top of it. So when I start to analyze data, I typically start in a Jupyter notebook. And what I will use is there's two drivers that I can use. One is called the ClickHouse driver. So that's a standard database client. You make a connection, you call a method where you supply a SQL command, you get back a result set, and it's usually one or two lines of code to pop that into pandas. So that's one way that you can get it. Another way is there's a SQL Alchemy driver. And SQL Alchemy is implemented pretty widely across databases. You'll use there's a percent SQL magic function that'll give you a result set, which again you can pop into pandas and begin operating on it. So those are pretty typical ways to get data out of the data warehouse. I think where it gets interesting is where you start to explore, hey, how much can the data warehouse do more for me than just dump raw data? Can I actually do some of the things that I want to do in pandas and do it in the data warehouse and save myself some time? So that's that's where you begin to dig into, okay, what can I do in the data warehouse that's actually going to save me time in Python?
And one of the potential issues that you might deal with if you're just trying to do, as you said, and just use the database as just a dumb storage layer and pull all the data back out into Python is running into the memory bottlenecks that we referenced earlier. And so what are some of the strategies for working around those bottlenecks, particularly if you're dealing with large volumes of data, and just ways that the data warehouse can help supplement the work that you would be doing within Python?
Yeah, I think when you start to frame it as like, how do I work with the memory I have available? At that point, you're asking the right question, because this is a problem that databases have fundamentally been occupied with since, well, at least as long as I've been working with them, so which is to say decades. So the idea, there's a couple different ways that you can think about this. What the data warehouse does is it basically allows you to access data that is vastly larger than the amount of memory that you have. And so there's like at least three different ways that you can think about using this. For example, if you need to do queries that only need certain columns, the data warehouse is going to answer those queries for you very efficiently. So instead of thinking of things in terms of being, having everything in a pandas data frame that contains all of the data in all the rows, just think in terms of having only the columns that you're working with, because you can get them very quickly out of the database, and if you need more, you can go back and ask for it. So thinking in terms of like, let's go and isolate the columns we're working with, bring them in, and then operate them on them in Panda. That's one thing we can do. Another thing that data warehouses can do very efficiently is downsampling. So SQL has this great feature called the materialized view. And the idea with a materialized view is that it is a different representation of the data that is designed to be more either smaller or more efficient because of the way it's sorted, for example, or the way that it's stored than the original source data. So, for example, if you're doing sampling off devices or collecting prices in the market, what you can do, if this is essentially going to be time series data, what you can do with a materialized view is you can downsample it so that instead of getting a data point for every time you do a measurement, you can actually reduce it to time segments, like 15-minute segments. This vastly reduces the amount of data that you collect. Moreover, with the materialized view, the database will basically do this downsampling at the time you ingest data. It does it once, so that if you then go to the view and ask for the data, you're going to get it back really fast, and you're going to get a much, much smaller amount of data that you can then operate on. I think what happens in pandas, if you just work off files, which is the way some of the pipelines work, you end up asking these questions again and again and again. So that's another important way that that data warehouses can help.
And also another Python tool that can help in terms of creating and maintaining those materialized views is the data build tool, or DBT for short, that will help in terms of ensuring that you have some measure of testing and consistency as far as processing the source data and creating the materialized views from it. And then also, once you have a materialized view, or even if you're just dealing with the table without doing any additional processing on it, one of the ways that it can help, from what you were referring before as far as pulling in window to time segments, is that you can actually let the database handle the cursor and feeding chunks of memory at a time, instead of trying to have to implement that logic yourself in your Python code to say, okay, I'm only going to process this amount, then I need to shift this out and then pull in the next bit. You can actually use the database as your working memory, pull in the piece that you actually care about for that particular computation, and then put it back into the data warehouse.
Absolutely, correct. And in fact, I mentioned that there are three ways that data warehouses can help. That sort of gets to the third. You can think of the data warehouse. You can think of, like, when you particularly as your data sets grow very large, you can think of this the raw data as existing in a window. So, for example, when you're collecting web logs, or you're collecting perhaps sensor data, the data that you collect that's newest is the most interesting. And what tends to happen is, after a certain period of time, that data becomes less interesting to keep around. So the data warehouse can do what you're describing at a very large scale, in the sense that you can put a time to live on data. This is a common feature in many data warehouses, so that your raw data will actually time out after some period of days or weeks or whatever you choose, and it just goes away. And the database does this automatically. So it's maintaining a window of the raw data that you can then jump in and look at, without you having to do anything special, like having complex pipelines or a lot of logic. The other thing is, then, with materialized views and other techniques, you can downsample, and you can actually keep those around for much longer periods of time. So I think when you combine these together, you then, in the database itself, it's kind of, holding your data in an optimized way that also builds, creates these windows that you can, so in effect creates these different granularities of data that you can look at. And then finally, to the point that you were making, database connectivity APIs are very good at streaming data. So, for example, in the ClickHouse streaming APIs, or the wire protocol, you tend to get data in chunks. So if you write your Python code well, you can basically get a piece of it at a time, process that, throw the memory away, get the next piece, so on and so forth. And this kind of buffering of data is something that connectivity APIs have been doing since the late 80s. The databases are really good and very well optimized for this problem.
And another case where the data scientist or the analyst might be leaning on Python is for being able to interact with tools such as TensorFlow or PyTorch for building machine learning models, which generally require a fairly substantial amount of training data. And I'm wondering how the data warehouse fits into that flow versus some of the other ways that they might be consuming the training information for building the models, either in these deep learning neural networks or in some of the more traditional machine learning algorithms that they might be leaning on scikit-learn for.
I think that's the place where actually we see the biggest gap in the technology right now. And what is happening right now is if you look at state of the art, and particularly among the people that I speak with, who in some cases deal with very large data sets, what they're typically doing is pulling this data out into Spark and doing their machine learning there, or they're pulling it out and doing TensorFlow. So you basically are taking the raw data, or maybe downsampled aggregates that are in the data warehouse, and you're just copying them out. You're running your machine learning on it, for example, training models, in which case you would just drop the data after you're done, or you're executing models, in which case you would score the data and maybe put it back in the database. So there's still a pretty big gap there. I think that as we go forward, I'm seeing two things which are really pretty interesting. One is that you're beginning to see the data warehouses uh, actually put at least basic machine learning into the data warehouse itself. So Google BigQuery is doing that. They have in databases traditionally have a create table command. They have a create model command, and so you can begin to run basic machine learning models there. The other thing that's happening is we're starting to see the emergence of other ways of sharing data between data warehouses and machine learning system. And these are represented in projects like Arrow, which is a columnar memory format that is pretty accessible from Python. And that's actually a project that's being driven by Wes McKinney, who's also the author of Pandas. And the idea there is that we're going to have common memory formats to make both transfer of data simpler, but also open up the possibility that we can now communicate through things like shared memory, as opposed to having TCP/IP streaming to move the data. So I think those are a couple of interesting things that are happening, but it's still very, very basic. And I think there's a lot more that we need to do to move that forward.
Another interesting development, too, is things like what Microsoft is doing with embedding the Python runtime into the Microsoft SQL Server to try and bring the compute directly in line with the data so that you don't have to deal with the wire transfer and serialization and deserialization itself.
Right. That's a really interesting that's a really interesting development. In fact, I think that's why one of the reasons why I'm very interested in Arrow is we call that kind of operation we call a UDF, a user-defined function, and databases like Postgres have had this for a long time. The ability to hook in, for example, C routines, but also Java and Python and other things like that. I think the problem that I see with this is that if you just do it in a naive way, that for every row you go and call Python, it's just horribly inefficient. Because the way that data warehouses operate on data efficiently is everything's an array. They basically break up the array into pieces. They farm it out onto all the cores that are available, and they just go screaming through this data to process it as quickly as possible. If you have to turn around for every value you have and call something in Python, that doesn't work. So I think I think and I'm not sure, I haven't used the Microsoft SQL Server capabilities, but I think what we need is something that allows you to deal with data at the level of blocks. And that's where I think something like Arrow, something that combines the capabilities of Arrow, where you can actually share the data formats, as well as the way that, for example, ClickHouse processes materialized views, where we don't just, when we populate a materialized view, we don't actually just do one row at a time. We do thousands or hundreds of thousands of rows at a time. So you have to think in terms of processes that allow you to do these operations on very, very large amounts of data using kind of a streaming processing model that allows you to get through the data really quickly.
And so, in addition to things like machine learning, where we don't have an excellent solution yet, what are some of the other limitations of data warehouses in the context of the Python data ecosystem, as far as being able to run analyses or some of the other data science workflows that somebody might be trying to perform?
Well, I think the biggest thing I see is there's just such a richness of things that you can do in NumPy and Pandas that still aren't fully supported in data warehouses. So most mature data warehouses will do a pivot, but for example, ClickHouse doesn't do a full pivot the way that Pandas does it. I mean, Pandas makes this so easy to do. And Pandas and Python in general has a wealth of statistical functions. So there are certain databases. So for example, KDB is a column-oriented store, or sort of a data warehouse that's is renowned for the fact that it has a very rich set of functions, but in general, the databases don't have the richness of statistical functions that you find in the PyData ecosystem. And I think that creates a problem because if you're looking to do, as you look at what people are doing with machine learning and data science, it's fundamentally driven by statistics. So if you don't have those statistics in SQL, you actually can't farm work out to SQL very easily. You either have to have user-defined functions and people add them themselves. As I mentioned, there's a lot of inefficiencies there. So I think this is a big gap. I think this is where we need to look over and see the good things that that are being done in Python and actually pull more of that stuff into the database and make the SQL implementation richer.
And in terms of overall trends in the industry and in the Python community, what are some of the things that you see going forward that you're excited about as far as the tighter integration of the PyData stack and data warehouses, and any challenges that you anticipate us running into as we try to proceed along that path?
Yeah, I think I think moving models into the database is a very interesting development. I'm a little bit skeptical that databases are going to be able to do this as well as Python does. And the reason is that for example, if you go to scikit-learn and you look at the models, they just have a raft of parameters that you actually need to be able to twist and turn to enable the model to give you not to be overfitted, not to be underfitted, and work effectively. The database implementations that I've seen have very limited parameterization. And so, for example, with BigQuery, as far as I can tell, it just kind of figures out, you give it the data to train the model, it kind of does it, but you don't actually know quite what it did to train the model. You don't have the full access to the hyperparameters that you would want to adjust to make the model work well. I think that's a problem, and it's not clear to me that data warehouses are going to solve this. I think that one of the really interesting questions is that we all have to work on is how can we take advantage of the fact that there are very, very powerful machine learning and deep learning systems that exist outside the database. How can we combine them? So instead of thinking about this data being pushed into the database, instead thinking about how these systems can work together. And so, for example, we have one of the ClickHouse users that I know. Their biggest desire is to be able to take a row of data, pass it to a model for scoring, and write that data back into the database all in a single operation. And so that's what we have to focus on to be able to I think to really join these two worlds together. It's problems like that, and we have to think about how to do it at scale. So, and I think there's some very interesting things that we can do. If you have data spread across many nodes, in many ways, this is not unlike what we had in the Hadoop file system, where you had data spread across a bunch of disk spindles, and you could send the processing down to go grab the data off those disks. So I think there's some things that we can do, but I think there's definitely some work to do to implement those ideas and really be able to join these two worlds together in an efficient way.
For anybody who wants to dig deeper into this space, what are some references that you have found useful that you'd recommend?
That's an interesting question. So I'm sort of into academic papers. I think one of the things that if you want to understand what a data warehouse is, I think just the quick, and you're reasonably familiar with data, I think one of the quickest ways to get up to speed is to go read the CStore paper by Mike Stonebreaker and a bunch of database stars. It was written by there's about 14 different people on the paper, but that basically described what later became Vertica. So it was a column store. It built on things that had already been done in the 90s, and then it introduced a bunch of other interesting things. I think that sort of gives you a notion of how data warehouses work and the kinds of things that they can do. Beyond that, I think the simplest thing is to go try them out. So ClickHouse, for example, is very easy to use. You can just, if you're running on Ubuntu, you say apt install ClickHouse server, it comes down. I think there are other systems that you can try out. So, for example, Redshift on on Amazon was really a complete groundbreaker in terms of ease of use. Just being able to click a few buttons and have a data warehouse spin up. BigQuery is the same way, and if you're on Azure, you can do similar things with the Microsoft equivalent based on Microsoft SQL Server. So I think just going and trying this stuff is probably the best thing to do, and just sort of begin to understand how you can actually use these systems. They're very accessible at this point.
And are there any other aspects of the overall space of the PyData ecosystem and data warehouses in general that we didn't discuss yet that you'd like to cover before we close out the show?
I think another place that there's sort of an interesting long-term integration, which is how we deal with data warehouses and GPU integration. So, for example, one of the reasons you go to TensorFlow is TensorFlow will has a much more efficient processing model with way more compute than we can get to when you're on conventional hosts. The data warehouses today are optimized for I/O. They don't necessarily have GPU integration. So I think that's another interesting case where we can, maybe some of that processing. If data warehouses begin to be able to take advantage of GPU, that may open up some other interesting opportunities for doing something, for sort of adjusting the split of where processing happens. So that's another thing that we're definitely looking at with a lot of interest.
Yeah, I know that there's been some movement in that space with things like Kinetica that is a GPU-powered database, but I haven't looked closely at it myself to be able to give any deep details on that.
Right. There's a database called MapD, which I believe is now called OmniSci. That's a really interesting space. And I do want to say that I've been sort of focused on moving things into the database, but I think that there's, just as PyData people can learn from what's going on in the data warehouse, because some of the problems, I think what's happening in the PyData space is people are beginning to recapitulate solutions to problems that data warehouses have already solved a long time ago. Sort of how to distribute data, how to sort of turn it into an embarrassingly parallel problem so you can get results very quickly. On the flip side, I think people in databases need to be looking very, very hard at the ease of use and just the wealth of operations that you can perform using the PyData ecosystem modules. NumPy, Pandas, Seaborn, scikit-learn. There's just so much stuff there that I think this is something that we can really learn from.
And for anybody who wants to get in touch with you or follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose a book that I've been reading called Foundations of Architecting Data Solutions. It's an O'Reilly published book, and it's been great for just getting a high-level overview about the things that you need to be thinking about if you're trying to plan out a new data infrastructure. So definitely recommend that for somebody who's interested in getting more into this space. And with that, I'll pass it to you, Robert. Do you have any picks this week?
I think my pick is going back and reading old papers. That's, as I say, the C-Store paper. I had it up preparing for this show. I love reading that paper. It's a really, really great thing to read. Beyond that, the books that really interested me are things like Python Machine Learning by Sebastian Rashka. That's something that came out. It's now in the second edition. I just got it a little while ago. It's not something you can read all at once. I just keep going back to it, and whenever I have time, I go look at what he has, sort of work the exercises and just try to keep learning more and more stuff about how to deal with data in Python.
Well, I appreciate you taking the time today to join me and share your interest and experience in the cross-section of data warehouses and the PyData ecosystem. It's definitely an interesting cross-section and an area that I am excited to see more development with. So thank you for your time and all of your efforts on that front, and I hope you enjoy the rest of your day.
Yeah, thank you, Tobias. It's always great being on your show.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.